Yeah, we were at Simon's algorithm, and the notebook were uploaded, I think, last week, right? Simon's algorithm. Can you all see the Simon's algorithm notebook? Okay. Oh yeah, I think we. But let me just quickly go over the algorithm again. Oh, I already share screen. I just need to do a slideshow. Right. Okay. Yeah, so Simon's algorithm is considering a problem that a function mapped to some finite set. And there is one hidden string so that the evaluation of f of x equal to f of y if and only if they differ by this bit string, bit y, bit string xor. Okay. So the question is to find this string. As classically, it's going to be exponentially hard because you need to go through many cases. So we won't focus on the classical part. We're going to focus on how to solve it quantum mechanically. And in the quantum solution, the complexity is proportional to the number of bits, as we will see, because you need to repeat roughly of order n time. Okay, so yeah. And there are a few observations which you can prove easily, and was actually homework of last semester's problem is that, okay, this is Hadamard gate apply to all the zero, and you know it's superposition, but if you have not zero, or it could be any bit string, it would map to this -1 s dot z. This is binary dot. And if you have a superposition, then this map to the sum of the two. The implication is that look at this, the sum here will vanish if s dot z is 1, right? So, and so if there are, if s dot z is 1, then this term's gone. So what you're left with are those z that are orthogonal to s. So we're going to use this property to implement the algorithm. Of course, you can also consider more general, right? It's s x divided by a bit string. So why we consider this is when you imagine run through the algorithm start with all possible superposition of your input, and then you do the function evaluation using this oracle. And then imagine you measure this, right? So we are promised that there's only two arguments that would map to the one solution, unless s is 0 identically. In that case, it's only one. And so we consider this, since we know there are only two, so when you measure, you would be collapsed to this. And this means the first register is always, when you measure in the computational basis, always orthogonal to the hidden bit string, right? So what you need to do is just repeat this many times. Each time you get a z which is orthogonal to s. The second time you get another bit string which may be equal to the first one. Then you repeat again until you collect enough. In this case, would be n-1 bit string. It's labeled as w, right? And then you have enough constraint. Now this w form a linear matrix. This times s will be 0. So you just need to find the s. Okay, so basically that's the algorithm. And I've uploaded homework, sorry, the notebook last week. Let me see. Stop share. Let me open. Okay. So everyone has the notebook? Yeah. Okay. Yeah. So of course, let me go through this. So of course, you import quantum circuit. Random is for you to generate the bit, hidden bit string. So this is so. For example, I'm using four bit. The problem is 4-bit mapped to another 4-bit. Secret bit string is 0 and 1, right? I want to have 4 bits, and these are random. And I define oracle. Oracle should map to a set where we want to construct so that only two map one. Okay. And so we come back to maybe oracle later, but assuming we have achieved that, there's a one example to do that. It's in this. So we're going to explain that. And then once we have the oracle, then we define our circuit. So here, I just look at the number of qubit in the oracle, okay? And the total number of register will be twice. The oracle, because it contains all the qubits, okay? So the number of first register is half, okay? And I define a quantum circuit. I have total number of qubits, same, but only have half classical register because I'm going to only measure the first register. In the algorithm, I assume that maybe if I measure the second register, I collect the first register to a superposition of 2. But doesn't matter how it collect, I always get 2. I always end up with, when I do the measurement, I always end up with W, which is orthogonal to the bit string S. So I don't need to bother to measure the second register. It doesn't matter how I measure, I will get. So that's why we don't bother to do that. So I only assign, and in my case, only 4 classical bits. So I prepare everything, this barrier just to show the structure. Now I get the oracle. Oracle here is a quantum circuit, right? In order to append the oracle to the circuit, we need to convert that first to instruction, and then we can append. And this is the number of range of qubit. It shows what qubit you apply to this oracle. Apply this oracle to. Okay, that's another barrier, and then you perform measurement. The measurement, right? Measurement here. Let's see, I'm a bit confused. Do I? Yeah, I need to do another Hadamard. This is because we do the Hadamard transformation in order to get. Wait, let me see. Let me first run this, and this is just to find the basis. I wrote this myself, and then I have the harder part for me to implement this is to write a classical post-processing, because the one that I got from Circ website, somehow it didn't work. This is the post-processing. Okay, the simulator. Oh, I changed my mind to change the number of qubits. Let me change it back. 4. Okay, so I ran 4 qubit and the solution 0, 0. Then okay, so something is wrong. Is something wrong? Oh, wait. Number of qubits. Can you run yours and see if yours fine? Oh, I think yeah. Let's just run it. Okay, so I ran again, and this time, so maybe the zeros case, some it shouldn't get zero. Yeah. So I am plotting the oracle. This is the oracle. So
Solutions also all zeros.
your solution is also all zero. And you get
The secret bit string get 11011.
it could be the classical solution is not, there's some bug in the classical processing. What you can do is you print out the count. Let's see. Okay, this one we get it correct. You can print results. You can print out the count. So this will show you the classical bit string that you measured. And then from here, you need to figure out what's orthogonal to that. Yeah. So yeah, I'm hoping because somebody could check the classical processing. Yes.
Professor, are you taking
Yeah.
the number of qubits to be 4 or 5?
Yeah, 4 here.
4.
Let me take 5. Solution, this solution.
Oh, I got a non-zero solution finally. 1001.
Also, maybe somebody could help check the classical processing part. Okay. Or let's check. See if anything I did it incorrectly. Right. Yeah. So we prepare everything, right? How the circuit probably is okay. And we apply this Hadamard to the first register. This is because we use this, right? If we have measured the second register, it would collapse to 2, and then we further do the Hadamard and then measure. So it could be the classical. If let's say if you get if you get 0 and not the correct answer, print out the count. Yeah, print out the count. Maybe the classical processing wasn't correct. And then maybe I will assign homework problem to fix it. But it's a classical processing part. But somehow it works most of the time. But I need to know what the incorrect case to debug. But okay, we can run a few. Let me use 3-bit. So these counts are you repeat and when you measure, it sometimes get 0, 1, 1, 0, 1, 0, etc. It was recording, repeating measurement, and this is ideal. So of course we won't get incorrect answer. So these will be bits that are orthogonal to the hidden one, secret one, and we get it correctly here. Okay, so I'm showing the oracle here. I'm using I have 3 qubit. So 3 qubit. This is my oracle. Cause we need to design the oracle so that we actually map 2 input to the same, not not more than 2. Okay. Otherwise you get others. And that we won't be able to follow the algorithm through. So the first 3 bits are the input, and the last 3 are the output. The value output. So if we do the control NOT here pairwise, we basically copy this bit information to the second bit. So here, up to this dash line here, up to this dash line here, this is just f of x mapped to x up to here, right? And we do another, this is the 0, 0, 1 here. We do a control NOT to make it 2 to 1. Let me see, I can explain. I can use this example to explain. Let me copy this. Yeah, it cancel, but it somehow make it 2 to 1. Let's do it here. Yeah, you're right. The two signal will cancel, but so if we imagine, let's just do example, right? So here, if we imagine we input everything, so up to here, we get 0, 0, 0, 0, 0. Okay, I'm following the order. I'm using this 0. Oh, I'm not sharing the right one. Need to share. Here. So if you input everything, this would be copy everything, right? Up to 1, 1, 1, 1, 1, 1, right? Because our design is we want to map to 2 to 1, but we're map 1 to 1. So in order to get rid of 1/2, we do a control NOT. If we do a control NOT, this thing get flipped to 0. So that's why they, right, you have this. If I consider the corresponding 1, 1, 0, it has 1, 1, 0. That's why, so I sort of use the GSZ like in entangling and then get rid of that. Yeah. Does that make sense? This example will explain. I mean, you could also have more. If you have more qubit, we can go back to look at other. More qubit, and you see, for example, I have, let's use 5. Okay, so I have 2 that are non-zero, so I have 2, right? And the design of this is to, okay, so up to here, right, up to here, this is up to here, this is just f of x equal to x, and here I'm selecting the first non-zero bit, using that as a control. So I use this control to this 8th qubit here, and then this one to the 9th qubit. So you see that I'm using this one to do the corresponding control now, just like what I just explained, the 3 qubit case. And I'm still using this one as a control now to the other. I'm not doing this one. I'm not doing pairwise. I always use the same control node. right? Imagine if you use pairwise and everything is 1, 1, 1, then you cancel everything. Then you only have one output, right? I'm saying if the hidden bit string is 1, 1, 1, what I would do is I will still start with the first one and then do control. Yeah. You can look at the structure of the code. So I first find a significant bit. So like here, I first find a significant bit. This is this bit. Okay. So 0, 0, 1. So this is this bit. So then I use this significant bit, do the control NOT with its corresponding output one. And I still use the control NOT. I use this significant bit as a control and do the control NOT to other bit that has 1. Okay. That has 1 because this the corresponding bit is here. This is just designing an example of this. There might be other way to do this. Okay, but this is more like a classical design of that function. Okay. If you find example that does not give the right answer, maybe keep a record of that and then see if you can help fix. It could be, I suspect, okay, so what I'm doing, I can explain to you to the code. What I did there is first, I wrote this part. So I collect all these bits, row wise, for example, these bits. So I collect all these bits, right? These are those that get measured, of course, except this one, we don't need to care about that. I collect all these non-zero bit string. I try to find the independent one. So just try to eliminate those are redundant. So basically what I'm doing here is do some kind of inner product. If inner product is 1, I subtract the component. Basically, I'm just taking a vector, take a second vector, inner product, if it has a component in, I subtract that from the first one, right? And I get the second vector. If I check if that second vector cannot be reproduced from the previous one, and I keep that, and I keep doing that until the end. This part I'm sure is correct. Then this was one that I found on the internet. People discuss how to do binary, so they use this SymPy. It's more symbolic NumPy. Then they do this null space. So maybe it could be this is also wrong here. Check. I think the only places could be this. Yeah. Okay. Then the classical processing really just find the basis and then do the null space. Okay. Any questions? Okay. That.
Also just
Yeah.
one. So in here, and when you're extracting this my list from the key,
What?
why are you reversing the order of the bits?
Oh, so yeah. So I'm reversing the order a bit because the convention using is IBM. Yeah. So the way IBM writes their output is Q0, Q1, Q2. It's not sharing screen. But I can just use here. Okay. So you see the print count, right? I have many counts. I have 0, 0, 1, 1, 1. in the IBM, this is representing as, so this 0 is actually the most significant bit. Actually, you should read it as 1100, 11000. But I just flipped, yeah, so that is easy to read. Because our bit string is 0011 hidden one. Our usual way of thinking is this would be 0001. So I want to have that. Okay, it's a convention, so and we will go back and forth between these two conventions. Yeah, this is something you have to keep in mind. So, and you can see in this code here, yeah, this is what I did, right? When I extract the characters, I sort of reverse order. It's okay if you don't do that, then you need to read the bit string backward. Because the reason is because when we implement this, this secret bit string, we treat that as this 0, 1, 2, 3. So we treat that as like this. But the IBM, so we, yeah. Okay. Here, the other screen. Okay, so yeah, this was what we started last week at the end of last week's. Yeah, so we're entering the third week. Okay, so we are discussing Grover's algorithm and then implementing that. So who still remember Grover's algorithm? What did you remember?
So Grover's algorithm basically
It's here, but yeah.
is a search algorithm,
algorithm.
quantum search algorithm on an unordered data list,
Mhm.
and it provides a quadratic speedup as compared to the
That's
linear
right.
speedup.
Yeah. So start from the beginning. Should start. Okay. Who else also remember Grover's? Yes. Yeah. What you can say whatever. Yeah.
I mean, just a bunch of like reflections,
Yeah.
a bunch of reflections.
Each
high probability to actually measure what you leave.
Yeah. Each step, how many reflections do we use?
It is two reflections. Yeah.
Two reflection. Each step, two reflection, and it become a rotation.
Oh, yeah.
Right. I cannot do a slideshow from this page. Okay, so this shift function. Fine. Let's go. Okay. So there are two reflections here. The first is the oracle. Oracle is function is to check if the item is the so-called mark item, and then put a minus sign on in front of the amplitude. So that's here. Okay. And then you do another reflection. This reflection in terms of the amplitude is called reflection with respect to the mean amplitude. And yeah, and then you continue. The effective action is a rotation, as I shown here, in the space of horizontal axis is unmarked item, the space of all unmarked item, and the vertical is the space of marked item. So I start with this in the equal weight superposition. So this is not normalized, but just for the demonstration. You do the reflection because if all code is reflection with respect to 0. So you put the minus sign, and here you do reflection. This is reflection around the mean. So I can mark here. So the mean here in the beginning, of course, is this, and the mean here you can see is not quite top, but it get reduced, right? It get reduced because of the two negative amplitude. And then when you reflect with respect to that, and it flip, these two lower negative one become higher. So that's these two. Okay, and then you do it again. You put a minus sign, right? Put a minus sign here and there, and then you do reflection around the mean, and then it keep getting higher, and then at some point it reverse the process and become lower and lower. Basically, it's like sinusoidal. Okay. Yeah, you can write, you can analyze this. We have done this last semester, so I'll just go quickly. We use this OF as the oracle. It put minus sign of my item because its identity is sum of everything. So that's why I need to -2 times the projector on the marked item.
Sorry, question.
Yeah.
The reflection, like it's an iterative procedure, right? Like the reflections, the rotation, and so on.
Yeah, and yeah.
So my question is the mean the updated mean that we're reflecting against?
Yeah,
or the original
yeah.
mean?
Updated.
So
Updated.
doesn't this mean I mean, isn't the whole point of the Grover algorithm just like align kind of like the wave functions like particular direction? So like it's very, if it's like a sinusoidal, like you just like overshoot very easily.
Yeah, but you don't, yeah, the angle is not necessary, it doesn't not necessarily repeat when you go back. It can shoot a little bit or undershoot it. So it's basically you keep doing this. Unless the angle is a rational over
I mean,
pi over 2.
Can I add something?
Yeah.
I think if you understand the geometric interpretation, so at the start, when we're starting with the plus state, that is the superposition of all states, the theta equals 0. And as we as we progress through the iterations, it's the theta that's increasing and getting closer to the mean. So I think in geometric interpretation, it's much easier to understand that as we iterate through the Grover iterations, it's the theta that's an indication of the mean. And the entire point of Grover's algorithm is that theta is approaching that marked state, and at pi by 2, ideally, that mean aligns perfectly.
but I understand that.
Yeah.
Question is basically when this theta prime, where theta prime is the theta of the last mean. If you reach like 50 degrees, then just overshoot it.
Yeah, you can
So
overshoot.
but we can like, just not clear to me why it's necessarily better to use the updated mean versus the original mean.
So the reflection is always doing the same thing, but it's just the interpretation of that step is with respect to the updated. Yeah.
But we could, in principle,
Like
use
here.
the original mean, just we would still like converge, might not be as fast as convergence.
Professor, did we not observe something similar in the adiabatic implementation, where if we were not updating the S state, the gap, the energy gap, we had a linear speed up, which was not really an advantage, but then we had to update that gap S.
Yeah, so when we are at that.
Yeah, and then we had a quadratic speed up.
Yeah, in the gap we would run slower, but outside we run fast. But I don't see the connection between the two. Yeah.
Okay.
But this if you want to keep, so you were saying you want to do the reflection with respect to
The original wave function.
this original wave
Well,
function. Which
original.
step?
I mean,
The here?
the mean of like a
So this
sigma.
one.
This is what causes it.
see, I don't know whether you can keep that information.
So, okay, so.
You may not, because you will need to copy some of the information in order to know.
Yeah, would be a technical limitation.
Yeah,
That would render this useless.
this would not be practical in a sense. You need to keep where that is in order to do the reflection.
Fair.
We only have one copy when we run
Okay,
the
I
program.
see.
But it's the interpretation is really this, right?
I mean, it would be
Yeah.
separate.
Interpretation is some of them reflect with some of the mean is really just this projections, 2 times the projection to the S minus identity. Really doing this, and this does not know anything about the state. Yeah. So that this is really a reflection with respect to mean. Whatever comes in and you apply that reflection, its interpretation in respect is the reflection with respect to mean. Yeah, only the oracle knows some information about the state,
Sorry, Professor?
but it does not really say the
I
state.
have a solution. So this is the value of theta.
Yes.
That is the sine inverse of n over m.
Right.
And if we go by the logic that has been provided, that if we say that we iterate with respect to this theta instead of updating it, so basically the number of iterations would come out to be simply pi by 2 divided by theta, right? Because the iteration,
No, you
because
mean
we're not
that-
updating, particularly updating the theta. And if I run an approximation, say, first approximation would be sine theta approximately equal to theta, and the other would be the binomial expansion. And this would give me something like pi m over n, which is not particularly an advantage. So the point stands that if we do not update the theta, we're not really getting a speed up, which is something that we observed in the adiabatic implementation of the Grover's algorithm as well. But to have a speed up, we need to update theta.
Yeah, I mean here we are doing we constantly updating
Yes.
the axis.
But
But yeah, but what I'm saying is, for that proposal, you need to keep the axis. You need to know what reflection you are doing, right? So
Yes.
you need to know the axis in order to you need to keep that, and that's not practical because we only have one copy of the state. In order to know the axis, you need to measure the expectation value and then extract the axis. Yeah. Okay, but this in a large number of items, and if you can consider the angle small, and then you get quadratic speed up. And the example of 4 item 1 mark 1, it is exact, like 1 step you'll get that. Okay. Right. So we can take a look of the notebook which I uploaded earlier this morning.
I apologize.
Yeah.
I know I'm more confused. Can you go back?
Yeah.
When you say that, like, this second, like the last equation, well, say the last equation,
Yeah.
iteration times theta plus theta over 2. Doesn't this mean we're reflecting against the original one? Because, like, if we're reflecting against the updated wave function, then we always change the theta that we're reflecting against, right?
So we always do Oracle, right? Oracle is doing this kind of reflection, and then we do these operation. It's called reflection with respect to mean, right? And you can see the interpretation. This is my at that moment the state, right? If you apply this operation, well, you look at the component after that, it's sort of 2 average of the component minus the input. So it's really updating according to reflection with respect to the mean before you apply that, right? Yeah, but I think it's better to have the geometric interpretation, right? this is really starting here. The starting point is theta over 2. And then doing these operation, fixed operation, right? It's fixed operation, really. And it's moving, advancing by an angle theta, theta, theta. And you really want number iteration times theta plus theta over 2 is close to pi over 2. So that's what you want. Basically, this is a geometric interpretation, perhaps. Is well, I mean, they're all equivalent, but it's hard to think in terms of amplitude wave function, but maybe this one's easier. And you just for the large n, you do the expansion, because this is an angle sine, and this, so when n is large, you get approximate, and you get a quadratic speed up. Yeah. Yeah, so from here, its rest is algebra. Right? So really, how much step you need to get to this vertical direction. Yeah, so this is what. But it only a special case you can hit pi over 2, and sometimes overshoot or undershoot a little bit, but which is fine. If you can get too close to vertical, it just measure, and there is a high probability if you repeat a few times, you get that. Yeah, okay. Yeah, so maybe don't get to I don't know, don't take this too seriously. It's just it's correct statement, but it just allow you to have these interpretation. So then when we use this to teach high school student, what we can say is that you just take all these, you can just ask them to flip negative and then do the average. But also this geometric interpretation also not hard. But we need to introduce these kind of interpretation that it's rotation, and some high school students may not have the matrices or they are not comfortable. Yeah. Okay. So maybe we can take a look of the notebook. Okay, maybe here, let me just mark check. Let's just make a remark. Check. Be incorrect. Before I move on, classical processing. Okay. The one, okay, this will be this one. This one is downloaded from IBM Learning Tutorial. If you want, you can click that. The page, the link here. This at this place here. IBM Learning. You can download. Yeah, this is where I download it. They let you know how much usage of QPU. So if you have account, you can try. 4 seconds won't cost you a lot. You're allowed to have 10 minutes each month. So take advantage of that. Okay. So
At that rate, can we do all four homeworks in like 10 minutes of 5 p.m. Runtime?
what 10 minutes?
You just mentioned, we have 10 minutes for free per
Yeah,
month.
yeah.
And if we're going to have weekly homework, we would have like 4 homeworks.
Yeah, I'm not asking you to submit to the real device.
All right.
Right. Mostly it will be simulated. Okay, setup, great. They already have robot operator. This is multiple, we've seen this, right? Kind of multiple control gate, decay. So in order to run on Unreal machine, we'll talk about how to run Unreal devices and using the sampler more in detail. Okay, this is just for the purpose of to find the back end, the machine that has the least job. For example, if you go to the website of the IBM when you log in and you click the machine, right? You click the machine and it will say how many 800 jobs. 800 job may mean that it's not likely to run this soon. So right, you need to check which machine has the least job, but you don't need to do it by hand. So the package has a function. You just say backend least busy one. Of course, you don't want simulator, then you say simulator false. Default probably will be that operations. True is yeah, and okay, the time I ran this notebook is from Keith, IBM Keith. This is the one here. Oh, this one has 37 jobs. Yeah. So I hope you can try the real machine, right? As when we will also try our homework. So this here, first define global oracle. Let's just take a look of how it did. So build a global oracle for multiple mark states. I so in that review, I didn't mention that because we may not necessarily know the number of mark items. So that require additional step. You need to estimate the number of mark item. It's called quantum counting. So you count how many solutions, but that requires phase estimation. Another way is maybe you have to estimate these rotation angle. Then you can estimate spending more measurement to estimate the angle. That could also be another solution for that. But here we will assume we know how many mark item. Okay. Okay, parameter mark state, string list mark states of oracle. So this is the input for the oracle, and the return is a quantum circuit. Okay, so it's a quantum circuit here, and what you would do is when you do that, when you append the oracle, you need to use two instruction and then append. Okay, so this is, it's not instance, it's not a list, then yeah, this just make it a list. Okay. Okay, compute the number of qubit in circuit. Well, it does not assume another qubit, it's just coming from the input string. So input string, and the length of that input. The first, they assume, okay, you see here, we assume all inputs they have the same number of qubits. Okay. So now we start creating the state quantum circuit. So mark each target in state in the input list. So in this list, flip target bit string to match Qiskit ordering. So here is also related to your question on the ordering. So they flip that. So right. So I didn't flip that. I flipped the answer. So they flip the ordering. So they put a minus sign. So if you input is 0, 1, 0, 0, so it just flip 0, 0, 1, 0. So for example, 0 indices, find the indices of all the 0 element in bit string. Okay. Add a multiple control Z gate with pre and post apply X gate, where the target bit string has 0 entry. So this is where they put a minus sign. So apply X to all the 0, compose multiple control gate, Z gate, and number of qubits. So maybe I want to go back here to the slide. So how do we flip the mark item? So how do we flip the mark item? If we know, how do we do that? Okay, let's say, how do we flip? Let me just draw. How do we flip a minus sign of some state? You know, example, right? Control Z is flip the sign. So just simple example, Control Z is to flip one, right? So you could have Control Z. This would flip 1, 1, 1, 1, right? So how do we use this to flip any bit string? A1, A2, and we're flipping 1, right? We're flipping all 1. So what we could do is just do some X on the 1 on some of these that are not 1, and then flip back again, right? That will be the one that you want to flip. So basically what they are doing. So maybe example is, so here we flip 1, 1 with put a minus sign. But if I put a X here and then here, which one get flipped? So 1, 1 will not get flipped, but if I have 0, it flipped to 1. Right? If I have 0, it flipped to 1. And then flip back to 0. But this bit string 0 get flipped to a minus sign, right? Instead of 1, 1. So basically, if you want a 0 here, then you apply additional X before and afterwards. So that's why they use the multiple control Z. Okay, I need to change the screen. Does that make sense? So it just need to have, yeah, have the know where the 0 is, right? And you do the X0
So that's what
before.
they were like mark,
Yeah,
whatever actually.
yeah,
Just like flip that
Flip.
direction space.
yeah. Put a minus sign
Yeah,
using these
whatever,
multiple.
flip
Yeah,
that direction.
yeah.
So you mean multiple control Z, if every one is 1, then you get a minus.
Multiple control. So this is the control.
Everything is 1, you get a minus.
Yeah. And it doesn't matter which user control, which is target, because it's all symmetric. But they use the first n-1 bit as a control, and this is the target. So they use this. We talk about these multiple classical control gate previously, right? So this is how they do the oracle, right? And the multiple control Z allow us to flip 1, 1, 1. But we can also use it to flip respect to plus, plus, plus. I'll come back to the,
You start a Hadamard gate,
yeah, so yeah, that would be a,
the multiple control J is not Hadamard gate.
no, multiple control Z is not Hadamard gate. There's, oh, yeah. Multiple control Z is control Z or control Z or control multiple control, right? These have to be 1 in order for the last Z to get flipped, yeah, to get applied. Does that answer your question? It's not Hadamard, but if you want to do the reflection with respect to this plus state, right? This is really a reflection with a plus state. What you can do is we do the reflection with respect to all 0, and then put Hadamard before and afterward. And how do you do reflection around all 0? You put all the X before and after. Right? If you use multiple control Z, right? You can do that. Okay, so we should be back here. So this is Grover's oracle. Okay, so yeah, if you look at the example, this will be the mark state. The way they do that is they flip this back, right? So their 0 is this one, 1, 1. So that they read backwards. Grover's oracle. So you make this oracle. Okay, maybe. Oh, did I actually run this? Oh, actually, I already ran that. Okay. Grover operator says in Qiskit's Grover operator, take an oracle circuit, return a circuit composed of oracle circuit, a cell, and a circuit that amplify the state modifier. This is saying that you could also do this using the Qiskit built-in operator. So this you build on your own, but you can also use Qiskit. You can decompose this. This will be similar to this. Let me run this. See what I get. Compose. If we look at here, it's doing this multiple times, right? Because you have to flip. You have 2 items to flip. So 0 and 1, 1, 0, 0. You can see it's one is here, some part of it. Okay, we use this. Some part of it, like the last bit, and then the second one is doing that for the second mark item. And here you see the Hadamard, I think it's Grover operator also do the reflection with respect to mean. And the last one here. Yeah, this is doing the reflection of mean. And they use control not, but this Z Hadamard flip that to Z, and then you have all these X that sort of do the reflection with respect to the plus. Okay, so this has additional reflection with respect to the plus. And here, these are just the, here we only have the oracle. Okay. And this is just computing the number of iteration according to use that sign formula, etc. Okay, the full global circuit. Just prepare everything. Global operator. So they switch to using their built-in operator. Okay, so for the exercise, what you could do is write the second half reflection with respect to the plus, which is the mean. Okay. Okay. So this is the circuit, including the measurement at the end. So because they measure all the qubit, you say measure all. If you only measure the first qubit, you would say measure, for example, Q0, or just the number 0. If the register has a name, you use that. Okay. And because they want to run it on real device, so they import something called task manager. So we'll discuss that later. And the target is the backend's target. You can print what exactly backend target is. If you want. It's probably the gate.
We use classical feedback.
There's no classical feedback.
No, that means if you want to make a multi-control gate, having classical feedback can make it more efficient.
If you want to set it again, multiple control gate and use.
They say that if you are using classical feedback, you can have fewer gates when making a multiple control gate.
Yeah,
Maybe
that's
they didn't take it into the package.
dynamic circuit. That's did they where did they say that?
I was just looking for this, but they are talking about a 4-qubit gate. So for 3, maybe we don't.
So where do you see that? It's not in this notebook. Okay, it's
not in the notebook.
Yeah. So let me not respond to that because
Yeah, that's a lot of the.
this if you copy everything from the stack exchange and you won't finish this. So yeah, does this show up what the target? Target I think would be again. It's not. So basically, you need to tell what machine you want to run and information about the backend. And you say what kind of optimization level. Optimization is they want to reduce as many circuit depth as possible. And then you have to run this. You use this task manager that run is to do these transpile, right? We talk about transpile. You could also just use transpile. And this task manager allow you to have more control. You can design how you want to optimize the circuit. Okay, and this is the optimized circuit. Let me just stop this interrupt. And what you can do, you can also ask, what is the size of the circuit, right? Or the depth of the circuit? Let's see if it's circuit ISA dot circuit depth or depth just depth. Circuit ISA, so maybe I didn't know this. Yeah, you can play along and then see what the circuit depth you get. This is 124. Let's see what. Let me just prove what the back end I have. So here is doing simulation. Maybe I'm simulation also as well. Okay, they are doing simulation and then the device. This is using the state vector sampler. To run the simulator, this kind of V2 version, we talk about more detail, is to give something called PUBs, primitive unified blocks. And this will be a list of tuple, and here is just a circuit. Okay, if you have many circuit, you would write in tuples. You usually will be a circuit. In the first will be circuit, and the second may be parameter, number of shots, and then it lists as a tuple. And if you have a second set, you have another tuple, and then everything as a list. So you run this. This is a simulator. So I can run this. And to run on the real back end, it's the same. It just you transpile to here. The simulator we don't have to transpile because it simulator knows all the basic gates, and the real device we already transpile, and usually just using the same command and run, and you get the result. Okay, using this command. If you don't know how to get a result, you can always go to once you run this, you can go to the IBM website, and you can see the job. Okay, so I was just running something, and this is the created. It took 2 days to run the job. 2 days and 3 hours, and it only ran for 26 seconds. Okay, so if you don't know how to retrieve the result, you go to this and you say you see it here. Yeah, you can just get the result from this. Let me scroll down there. It will tell you how you get the result. Job, result, etc. It depends how you write and what are you using. We're using sampler or you using the estimator. So yeah. So we'll show you also what kind of job you run, but we can discuss that maybe later. Okay, so post-processing. Oh, and I actually run this twice. That twice took 2 days to finish. So previously I only have one result, and I have 2 results, so I load both of them. Simulator is the blue because the ideal only 2 mark items appear. I ran this first time. This is an orange. Second time was the one that took quite long. I think the second one seemed better on average because it represents these mostly equal weight for the mark item, although still quite noisy. But as we expect, what is the circuit depth? I forgot. It's quite long, right? Um,
24.
and that's not bad in the sense 120. Yeah. So the device actually is improving. So
What are the factors that the result are not perfect, right?
Yeah.
Like, what are the main cause of, this?
This will be usually the many factors, state preparation, the state may not be perfect, but the error is low and a gate error. Usually it will be 2-qubit gate error. And also the coherence and then readout error.
How long is the whole operation? It's like one shot.
One shot will be much smaller. Like this, the one that I get here.
Well, units of like coherence time of like.
Well, coherence time
IBMs.
probably a few 100 to 1,000 nanoseconds.
How long is the
Each run probably
one line?
depending on the circuit depth, yeah. Gates, single qubit gate will be of order nanosecond or 10 nanosecond. And
So
2-qubit gate,
It's the same scale as the coherence time, basically.
it depends on the machine. Yeah, this you could go
Order 1 units.
to the machine here. This run on Brisbane. You can check what Brisbane's property. So let's just say T1. Oh, T1 is quite long. Right? Yeah, this machine's dramatically improved from the old one. My data that I told you was old. This T1 is 200 microsecond. T2 is quite long.
So
Their gate are nanosecond scale.
coherence time is not an issue.
Yeah, maybe not in.
So it's just a 2-qubit error.
It could be a 2-qubit error. We'll see. Using the wrong 2-qubit error. If you see this one, the mean is roughly 8 times 10 to the minus 3. But depending where you select the qubit, and yeah, it might. Usually in the past, what we did is before we run the job, we go through this. Which one has a higher or smaller? We would select one that has smaller, and then we run. But sometimes it can change after calibration. It show up. The error rate is different for different. Yeah. Okay.
Do they do error correction for you?
No, no, there's no error correction. Yeah, there's some error mitigation we can talk about that later. But there's no error. I mean, the error correction is still really at the research and from there still implementing things.
Professor, do they provide some information on the gates? For instance, some processing time of the gates that could help us understand how the error is correlated with the circuit depth?
There's no information from their public website here. They provide the basic information, right, about the device. 1 qubit, 2 qubit, these information. So in order to say what caused what, you probably have to run and design the circuit yourself. Yeah. So in the past, we have designed things to measure the error from the measurement, like readout error, 0 and 1. Do you trust is 0 or is it 0 is really 0, 1 really 1? So we sort of propose something that allow you to characterize that, and then using that to also do the mitigation. Happened that around the same time, IBM was also thinking something similar. So it's now like readout. Yeah, there's some information there. So now readout mitigation is a standard here in IBM, but it only apply to estimating some estimating some observable. I think readout may not apply to the probability distribution. I need to check. You could also have that. And therefore, in homework 2, we have that. I should make that visible now. Is it there in the website? But homework 2 is about measurement. So I'm going to show briefly the measurement. This was taken from the Qiskit book, old Qiskit book, but I make sure it can. So there's 5 small problems. Initialize creating a circuit and measure XYZ, right? It's quite simple. And see what's okay. You just problem 3. Yeah, 3 is here. Here I introduced the readout since you asked. This will be, so the way to do that is you prepare 0 and then you immediately measure 0 or 1, right? So that you get the probability of 0 turn to 1, 1 turn to 0, and then you prepare 1. You measure to see the count of getting 0 and 1. Of course, this assumes that the state preparation is better, has a lower error rate. And then you sort of do the inversion of matrix. So yeah, and there are more complicated scheme. So you would work through that here. And what else? Yeah, and there's some example of measuring energy by getting the distribution and estimating the observable. Okay. Yeah, and there's a Bell states and measure the observable for Bell states. Yeah. So this will be, I'll make this available today. It's not hard, just, yeah, guide it through that. We are already looking at notebook which are more complicated than the homework. Okay. Okay, any other questions?
I have a question about
Yeah.
part 5.
Part
Can
5.
we use problem part 5? So can we use observables instead of implementing the right quantum gates before the Z basis measurement? Like
Oh,
we
you
do
could use, I
have,
mean, you could use observable, but here we are not using the primitive called estimator. So we are really just basically getting a distribution.
okay.
Yeah. Yeah. Okay. 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 So that's it for today.